Welcome to AEL. Today, we are going to build a powerful automatic water level detector system using the heart of the Arduino Uno, a bare ATmega328P microcontroller, along with a 16 MHz crystal. This isn't just about plugging things into a board, it's about creating a custom, compact, and efficient circuit from the ground up. First, let's look at the key components, with a special focus on our core microcontroller. Our central processing unit is the ATmega328P. It's a 28-pin DIP-type chip that will run all our logic. For easy identification, just follow the pinout on your schematic. For example, C1 and C2 on the Proteus schematic correspond to pin PB6 and PB7 on the ATmega328P, or pin 9 and 10 on the chip. You can find a full datasheet using the link in the description. For programming the ATmega328P, we can use an Arduino board. This is an easy way to write and upload your code to the microcontroller using the Arduino IDE software. When using the ATmega328P, you need an oscillator circuit. This is achieved using a crystal oscillator and stability capacitors. As proposed by the datasheet, we will use a 16 MHz crystal and two 22 picofarad capacitors. For our display, we will use a 16 by 2 LCD to show information about the water level. We'll use red, yellow, and green LEDs to indicate the water level when it is high, medium, or low. For our pumps, we will use two DC water pumps, where one acts as an inlet pump and the other as an outlet pump for our water tank. If you need to use a larger pump, you can connect a relay and use an AC power source, which will enable it to handle a larger current draw. We will use a bipolar junction transistor, which will act as a switch, receiving commands from the microcontroller. We'll also use a diode to provide a return path for the energy stored in the relay coil, which protects the transistor from high inrush current when it turns off. For added protection, include a 10K resistor at the base of the transistor to limit the current flow. Now for our water level sensor, please note, I'm using an LDR, or light-dependent resistor, in the Proteus simulation because it doesn't have a specific water level sensor. This is a good way to understand the concept because a water level sensor is an analog sensor whose output signal depends on the variation of its resistance. When placed in a container of water, as the water level increases, its resistance decreases. When the water level decreases, its resistance increases. The LDR has the same operational principle, but it works with light instead of water. So, for this lesson, you can mentally replace light with water. When the light intensity increases, it implies the water level is rising. When the light intensity reduces, it implies the water level is falling. For our power supply, we need 12 volts, so we can use a battery and a voltage regulator to provide a stable 5-volt supply to our components. So let's start with our schematic connection in Proteus. We will begin with the indicator LEDs. First, connect the 5-volt power source to the collector of a transistor. The emitter of the transistor connects to one end of a 220 ohm resistor. The other end of the resistor connects to the LED's anode, and the cathode of the LED connects to ground. We'll label the base of this transistor LED 1. Also, connect a 10 kilo ohm resistor from the base to the ground. This completes the circuit for our low water level indicator. We will repeat this same process for the mid-level and high-level indicator LEDs. The bases of the transistors for the low, mid, and high water level LEDs are connected to the ATmega328P's port B, specifically to pins PB3, PB4, and PB5, respectively. Now, let's add a tank to our schematic for a better visual explanation. We'll place the inlet pump and the outlet pump. For the pump circuits, we will use a transistor, a diode, and a relay. The base of the transistor for the inlet pump circuit is labeled pump 1, and the base of the transistor for the outlet pump circuit is labeled pump 2. These are connected to the ATmega328P port D, on pins PD0 and PD1, respectively. For the sensor, we connect the LDR between a 5V source and a 10 kΩ resistor. In between the LDR and the resistor, we connect our analog input pin, PC0 on port C. This is an analog pin on the ATmega328P. Also add a voltmeter to show the voltage variation as the LDR's resistance changes. For the LCD connections, the LCD's RS, E, D4, D5, D6, and D7 pins are connected to the ATmega328P port D, on pins PD2, PD3, PD4, PD5, PD6, and PD7, respectively. We will also connect the LCD's contrast pin to a potentiometer, which is then connected to a 5V power supply. For the main power supply, you can use a 12V DC source, such as a battery. Notice that most of our circuit components require 5V. To handle this, we will connect a voltage regulator to our 12V source. This regulator will step down the voltage to a stable 5V to power all the other parts of the circuit. Finally, for the ATmega328P itself, we'll connect the VCC pin to 5V. The 16 MHz crystal and its 222 picofarad capacitors are connected to pins XTAL1 and XTAL2 to provide our clock signal, which is essential for the microcontroller's operation. Alright, let's dive into the code that makes our automatic water level system work. The goal of this program is to keep the water level in our tank within the mid-range. When the water gets too low, it turns on the inlet pump to fill the tank. When it gets too high, it turns on the outlet pump to drain it. Let's break it down section by section. First, at the very top of our code, we include the liquid crystal library. This library is essential for communicating with our LCD screen. Next, we define all the pins we are using. These are the connections between our microcontroller and our components. Liquid crystal LCD 2 to 7 tells the program which pins on our microcontroller are connected to the LCD display. Initialize LED 1, 2, and 3 to pin 11, 12 and 13 respectively. LED 1 is for a low water level, LED 2 for a mid-level, and LED 3 for a high level. Initialize pump 1 and pump 2 to pin 0 and 1 respectively. Pump 1 is our inlet pump, which fills the tank. Pump 2 is our outlet pump, which drains the tank. Initialize port to pin A0. This represents our water level sensor, which is an analog sensor connected to analog pin A0. In our simulation, we use an LDR to mimic this, but the principle is the same. It gives us a varying voltage based on the water level. The setup function runs just once when the microcontroller first turns on. Pin mode is a command to tell the microcontroller whether a pin is an output or an input. The LEDs and pumps are all outputs because the microcontroller is sending a signal to them. The water level sensor is an input because the microcontroller is reading a signal from it. LCD begin, 16:2, initializes our LCD screen, telling it that it is a 16-character by 2-line display. The next few lines display a welcome message on the LCD, giving us a brief moment to see that the system has started correctly before clearing the screen. The loop function is where the magic happens. It runs continuously, checking the water level and adjusting the pumps and LEDs as needed. Initialize port value to read the raw analog value from our water level sensor. This value will be a number between 0 and 1024, with 0 typically representing the lowest level and 1024 representing the highest. Float port volt and convert the raw value into a more meaningful voltage reading. Since our microcontroller operates at 5V, each step on the 1024 steps is about 0.0049 volts. This conversion helps us define our water level thresholds in a clear and consistent way. Now for the main logic, which is handled by 3 if statements. The system is designed to maintain the water level in the mid-range. If pot volt greater than 4.5, checks if the voltage reading is above 4.5 volts, which we've defined as a high water level. Inside this if statement, we execute a few commands. We turn off the inlet pump, turn on the outlet pump, and light up the red LED to indicate a high-level alert. If pot volt greater than 2.0 and pot volt less than or equal to 4.5, checks if the voltage is between 2.0 and 4.5 volts. This is our target range. Inside this block, the most important thing to note is that we don't activate either pump. This is because the water level is already where we want it to be. We just turn on the yellow LED and display water level MID on the LCD to let us know the system is stable. The else statement turns off the mid-level LED if this condition is false. If pot volt less than or equal to 2.0, checks if the voltage is 2.0 volts or lower, indicating a low water level. In this case, we turn on the inlet pump to start refilling the tank and turn off the outlet pump. We also light up the green LED. The LCD displays water level low and the current voltage. The else statement ensures the low-level LED is off when this condition is not met. The entire loop function repeats thousands of times per second, ensuring our system is constantly monitoring the water level and making real-time adjustments to keep it in that ideal mid-range. Let us compile the code and take the hex file to our simulation. So let's run our simulation to make sure it functions as expected. We display our initial text, "Welcome to AEL." If you have come this far, don't forget to like and subscribe. Initially our sensor read the water level and sent to the microcontroller. If the water level is below 2, we turn on the inlet pump to start refilling the tank and turn off the outlet pump. We also light up the green LED. The LCD displays water level low and the current voltage. If the water level is between 2 and 4.5, we just turn on the yellow LED and display water level mid on the LCD to let us know the system is stable. As the inlet pump continues to float in water, the water level goes above 4.5. We turn off the inlet pump, turn on the outlet pump, and light up the red LED to indicate a high-level alert. We also display the message, water level high, on the LCD. And there you have it. You've just learned how to build a complete automatic water level detector and control system from scratch, using a bare ATmega328P microcontroller. We covered everything, setting up the bare chip with its 16 MHz crystal, understanding the circuit connections for the LEDs, pumps, and LCD, and thoroughly dissecting the code that intelligently manages the water levels. You now have a solid foundation in custom microcontroller circuits. The complete code for this project is available in the description below. If you found this tutorial helpful and inspiring, please give this video a big thumbs up and share it with anyone who loves electronics or wants to dive deeper into microcontrollers. Your support helps us create more content like this. Comment below if you'd like to see a full, working physical prototype of this exact circuit. If there's enough interest, I'll put it together in a future video. I highly encourage you to try building this yourself. The best way to learn is by doing. And remember, the beauty of open source electronics is that this isn't a rigid design. You can easily edit the code to change the high and low water level thresholds, swap out the pumps for different types, or even add more indicators. You could even integrate IoT functionality to receive water level alerts on your phone or control the pumps remotely. The possibilities are endless. Thanks for watching, and happy building.